energy, power.
Sir, new chapter.
New chapter. We know work is a product of force into displacement. Already we have discussed, when we compress a spring, a work is done and there is an energy stored. That means this work we cannot compare with the work in our work means, here you can see in physics, work means there should be a force, there should be a displacement, and there should be a change in energy. Either energy will be in the form of potential energy or energy will be in the form of kinetic energy. A spring, if you compress, a work is done. Here by the external agent, and outside someone should compress it. Automatically it won't compress. In that case, you can see energy stored in it. If spring is released, spring does the work. That time energy used, you can see spring moves. Here kinetic energy is developing. So you can see that work is a product of force and displacement in the direction of the force. And whenever there's a work, there's a change in energy you can observe. This is a work in physics. It's not like ordinary work you're doing. Okay, right now. Work is a product of force and displacement in the direction of the force. It is a product of force. It is a product of force and displacement. It is a product of force and displacement in the direction of the force. Let F is a force acting on an object. Let F is a force acting on an object at an angle theta, at an angle theta, at an angle theta.
Sir,
let F is a force acting on an object. F is a force acting on an object at an angle theta with respect to the displacement S. With respect to the displacement S. Then work done W is equal to Fs cos theta. Fs cos theta. Unit of SI unit of work is joule. SI unit of work is Newton meter or joule. Joule.
So work Newton meter.
Newton meter or joule. This Newton meter only known as joule. Clear? Now, 1 joule, if F is equal to 1 Newton, right, if F is equal to 1 Newton, S is equal to 1 meter, theta is equal to 0, then W is equal to 1 joule. Then 1 joule can be defined as 1 joule can be defined as 1 joule can be defined as that amount of work done, that amount of work done, so that 1 Newton force exerting onto a body.
Sir, can you repeat 1 joule can be defined as the?
1 joule can be defined as the work done so that 1 Newton force displaces a body through 1 meter in the direction of the force.
Sir, onto a body displaces it
in the direction of force. Then there are 3 types of work. positive work, zero work, and negative work. And negative work.
The positive work and
So positive work, zero work, and negative work. Positive work, zero work, and negative work. Now positive work. Positive work. Look here. If this is the force F, this is the displacement S, then W is equal to Fs cos theta. Until 0 to 90, if you substitute any value, answer will come positive value. This kind of work is known as positive work, right? Right now. If the angle between force and displacement is acute, if the angle between force and displacement is acute, the angle between force and displacement is acute, then work done is called positive work. If the force and displacement, angle between force and displacement is acute, then work done is known as positive work. Example, pushing a object or pulling an object, anything you can write. Next is zero work. Zero work. See, when work is zero, you can see there won't be any energy change. Some examples I will tell you. Look, this is the wall of a room. You are pushing it. You are exerting force. Work is equal to Fs cos theta. You are exerting force, but object is not moving. We can say impending motion. This time, no work is done. Another example, in a conservative field, an object is thrown up. So work is done, going up. While coming back to this point, displacement is zero. So how much potential energy gained? That energy is used. So here W is equal to F is there, but net displacement is zero. Therefore again work done is zero. If object stop here, it has a potential energy. If object come back, that same energy is used. Clear? Another example, suppose this is a nucleus. Electron moves all around here. Electron is being attracted here. This is a force of attraction. But electron moves always tangent to the surface. You see? Like this, tangent. So here you see, either electron is not going in the direction of force or opposite direction of the force. Angle between velocity and the force is 90 degree. That means Fs cos 90 0. But if the electron, if you supply an energy from outside, it will go to next orbit. Now we can say work is done because this electron moved opposite to the force. If this is losing energy, it will come to inner orbit. Now we can say work is done. But as long as it's in the same orbit, no work is done. Similarly, around the sun, if planets are moving in an elliptical orbit, okay, in an elliptical orbit, it is just like throwing an object. See, here attraction is less. Now attraction increasing. Here it comes an energy. Now again it's going opposite to the attraction. So same, this much energy will gain here. Same energy will be lost here. Same energy will gain here, like that. So total displacement is zero. There also net work done is zero for a complete cycle. But here to here there is a work is done because see distance from the sun to that planet is reduced. Then work is done. Otherwise, if you make a complete orbiting, net displacement is 0, no work is done. Clear? These are the examples of zero work. Write down. If zero work, we know W is equal to Fs cos theta. If F is not 0, but displacement is 0. Example, impending motion. Impending motion. Then work done is 0.
If S is 0 or F.
W is equal to Fs cos theta.
The force is not 0, force is 0.
Force is not 0, but displacement is 0. Then it is called impending motion. Then work done is 0. Now, in a conservative field, next day, this is the first example. Second example, in a conservative field, if net displacement is 0, if net displacement is 0, then work done is equal to 0. In a conservative field, if net displacement is 0, then work done is 0.
So what is conservative field?
Conservative field, their energy is not lost. We have discussed no. Conservative field and non-conservative field, no. Conservative field is a field where no energy loss. Example, gravitational field. When you lift an object, energy is stored. When you release an object, same energy is used. But on a floor, say friction. Here I am pushing an object to here. It will not come back to its own place because that energy is lost on the spot in the form of heat or sound. So friction is non-conservative. Their energy will not be stored. Clear?
Gravity is conservative, sir. Any other conservative examples here?
Spring force. Conservative force. When you compress, your energy is stored as potential energy. When you release it, that will convert again back to kinetic energy. Electrostatic force. This you have to exert force from external agent to bring them closer. If you release it, they will go automatically. In these cases, I know it's conservative force. Two magnetic poles, example. Okay? You understand?
Yes, sir. Understand it.
Yeah. So here, work done is 0. In a conservative field, if net dipole moment is 0, work done is 0. Example, an object is thrown upward and come back to its initial position. Example, an object is thrown upward to height and come back to its initial position. Net displacement is 0. Okay? Or an electron moves along an orbit. That is another example. Leave it. That another example. Then this one. Planets moving around sun in elliptical orbit. Planets moves around the sun in elliptical orbit. Planets move around the sun in elliptical orbit. For its complete revolution, half the way work is done. For its complete revolution, net displacement is 0. Then no work is done. For its complete revolution, net work done is 0. Then no work is done.
Sir, in the non-conservative field as well, work can be 0, right?
Friction. Non-conservative field is friction. Next, another example for work done. If angle between force and displacement is 90 degree. if angle between force and displacement is 90 degree, then work done is 0. W is equal to Fs cos 90, that is 0. Example, an electron moving in circular orbit. Your centripetal force due to electrostatic attraction is perpendicular to displacement. An electron moves in a circular orbit around a nucleus. Your centripetal force due to electrostatic force of attraction. Electrostatic force of attraction means between proton and electron. The force between the force of electrostatic force of attraction between proton and electron is perpendicular to the displacement. Is perpendicular to the displacement.
So here
Force, electrostatic force between electron and proton is perpendicular to the motion of the electron in the orbit. Okay. Negative work. Negative work. If the force and displacement make an angle obtuse more than 90, if the force and displacement, this is force, this is displacement, this is force of friction. If the force and displacement makes an angle obtuse greater than 90, then work done is negative. That means W is equal to Fs cos 180 minus Fs. Okay. Next, identify.
So if I move a box through the floor, then it is negative work, right?
With respect to friction, negative work. With respect to a muscle, positive work.
Okay, so
Identify the nature of work in the following situation. Identify the nature of work in the following situation. Okay, write down. A situation I'm telling you, you should tell me which are the cases: positive work, zero work, and negative work. Okay, look here now. Then you will get clear idea what is it. A boy lift a bucket of water from a well. Lift a bucket of water from the well. Boy lift a bucket of water from a well and walks along a horizontal road. And walks along a horizontal road. And walks along a horizontal road. Climbs up a ladder. Climbs up through a ladder to a height h. Then keeps the bucket of water down. Keeps the bucket of water down to the earth. Identify positive work, zero work, and negative work in this situation. Okay, look here. This is a well. From this well, this boy lifts a bucket of water. Okay. Now, first one. With respect to his muscular force, work done is positive.
Positive. Yes, sir.
No, right. First one. With respect to the muscular force, work done is positive. First one. With respect to gravitational force, work done is negative. So you have to explain with respect to which force, always. With respect to gravitational force downward. With respect to gravitational force, work done is negative. Because theta 180. When he walks along a horizontal road, with respect to gravitational force, theta 90. With respect to gravitational force, theta 90. Therefore, work done is 0 with respect to gravitational force. With respect to his muscular force, he is pushing it forward. With respect to muscular force, work is positive. With respect to frictional force, work is negative. Next para. When he climbs up, with respect to muscular force, work is positive. With respect to gravitational force, work is negative.
Sir, muscular force is negative.
Positive, right?
So while he is climbing up, the muscular force is 0 work done, right? With respect to muscular force.
No, he is going opposite to gravity, right? The way he has to exert force going upward, then only he is going upward, right?
With respect to muscular force, the work done is 0.
No, positive. Work done is 0 means he will not move, right?
Yes.
With respect to muscular force, suppose he is climbing. While climbing, he has to exert force upward, right?
Yes, sir.
But with respect to gravitational force, it's negative.
Yes, I understand that.
When he's keeping the bucket down, with respect to muscular force, work is positive. With respect to gravitational force also, work is positive. Next, studying conservative and non-conservative field. Conservative and non-conservative.
Sir, what about keeping the bucket down on the floor?
Positive work. With respect to muscular force, with respect to gravity. Both are in same direction. Positive work. Now, conservative and non-conservative field. Look here. See, conservative field means energy will not be lost. Therefore, work done is independent of path. For example, look, here, this is an object of mass m. Force acting downward is mg. If you want to lift this object to a height h, how much force you have to exert onto it? Without acceleration. If you want to lift this object to a height h without acceleration, how much force you have to exert?
mg.
Mg. Equivalent opposite force you exert, it can go up without acceleration. Suppose in this direction, we shifted it to a height s is equal to h and theta is equal to 0. Now, if you calculate work, W is equal to force into displacement. Force you exerted is mg, displacement is h, isn't it? mgh. This is the work done. Agreed?
Yes, sir.
Now, that derivation we'll do later, but now we'll come to this point. What is a conservative field? This is an object. First I'm lifting to a height h1. Then this is moving.
Rahis, please mute your mic, bro.
Draw the diagram. A, B, C, D, E. Okay. This is height H1. This is height H2. Your weight acting is mg. By exerting an equal and opposite force, a work is done. That is W1 mgh1. Okay. This is a force exerted. So mgh1. This is 90 degree. Theta 90 degree. Therefore, work done is equal to 0. Here again, W3 is equal to mgh2. Here, theta 90 degree. And W4 is equal to 0. Okay? You understood that?
Yes, sir.
Now you can see that total work done in lifting the object along the path A, B, C, D, E. A, B, C, D, E is equal to W1 plus W2 plus W3 plus W4. So W, A, B, C, D, E is equal to mgh1 plus 0 plus mgh2 plus 0. Then here W, A, B, C, D is equal to mg into h1 plus h2. This is equation number 1. If we lift this object A, B, C directly W, A, B, E, then this is mgh1. And here to your h2, right? Height, same height, plus mgh2. Then answer is mg into h1 plus h2. This is equation number 2. Equation 1 and 2 shows that W, A, B, C, D is equal to W, A, B. It is independent of path. That means, suppose you are taking a bucket of water and taking this way and pouring the water in this tank. And here directly a person go here and putting water in this way. Both will have same energy. Since you walked more distance, you won't gain more energy. Clear? Do you follow?
Yes, sir.
Yes, sir.
In a conservative field, when you calculate work done, shortest distance you have to choose. From initial point to final point, shortest distance you have to choose. Clear?
Yes, sir.
Yes, sir.
So have you written the definition for conservative field?
No.
Right. Conservative field is a field in which work done is independent of the path. Conservative field is a field in which work done is independent of the path. and energy is conserved. And energy is conserved. Next para. Conservative force is a force. Conservative force is a force by which work done is independent of the path. Work done is independent of the path. Example of field: gravitational field, electrostatic field, magnetic field, etc.
Sir, by which the work done is independent or dependent?
Independent. It's not depending on the path. Example of field: magnetic field, gravitational field, electrostatic field. Even spring, field of spring. And force: electrostatic force, gravitational force, or spring force. Anything you can say. Then proof. This is a proof for work done is independent of the path. Finish this proof. First one, what is this? Work done taking the object along A, B, C, D, E. This is the work done in taking the object directly A, B, E.
Sir, what is the conservative field?
Conservative field is a field. Example you mean?
Sir, definition.
Definition. It is a field in which work done is independent of the path.
Oh, okay, sir.
So it's time less than 1 minute. Next class will continue, okay? One more, if possible, you write. Non-conservative field is a field in which work done is depending on the path. Example, friction. Okay? Conservative field is a field in which work done is depending on the path. That is non-conservative.